So I ended my last video a little too soon. I turned the page and I found this gem of a problem that I wanted to share, referring to conditionally convergent series versus absolutely convergent series. So with a conditionally convergent series, you can do some strange things. So here's a proof, I put in quotes, that 1 equals 2. Okay, that seems weird. So let's walk through it and see if we can find the flaw. So 1 minus a half plus a third minus a fourth plus 1/5, that's our alternating harmonic series, right? We were discussing that on the previous video, has a certain sum, okay? So let's assume that sum is S. If I multiply both sides by 2, then I have 2S. That's 2, this is 2 halves, 2 thirds, minus 2 fourths, plus 2 fifths, minus 2 sixths, and so forth. And if I group some of these terms, so if I take these two, that's 2 minus 1 gives me 1. And then I put the minus 2 fourths. And then I take the 2 thirds minus the 2 sixths. And if you do the algebra there, that's really 1/3. Then I'll take, at some point, I'm going to have a minus 2 eighths. So all that reduces to negative 1/4. If I take the 2 fifths and the minus 2 tenths that I'll get at some point, that gives me positive 1/5, and so on. So I can recreate by, in some cases, combining a couple of these fractions, I can recreate the series I started with, which is S, right? I called that sum S. But the left side equals 2S. And if 2S equals S, and you divide by S or move it over, in fact, that's telling you 2 is equal to 1. What? Right? So clearly there must be something wrong. So the flaw in our argument is, again, since S was a conditionally convergent series, we talked about on the previous video that a conditionally convergent series doesn't have a unique sum, right? Depending on how you add the terms. So when we get 2S equals S, that is totally possible because we rearranged the terms to get 2S and we got a different sum, right, than the original sum. So we're not talking about the same sums when we get to that point in the quote unquote proof, right? They're different sums. And again, just to emphasize, here's a specific example of an absolutely convergent series, the alternating p series 1 over n squared, 1 minus a fourth plus 1/9 minus 1/16, and so forth. If you try to do some proof like we just did there, by rearranging the terms, it isn't going to happen because, again, the property of an absolutely convergent series, no matter how you rearrange these terms and add them together, you're going to get the same sum every single time. Okay.